So good day everyone. Today we are going to discuss about quadratic inequalities. So by definition, a quadratic inequality is an equality of degree 2. It means that a quadratic inequality is like a quadratic equation, but it contains an inequality sign like the less than, greater than, less than or equal, greater than or equal, and not equal. So technically, when we talk about quadratic inequality, it means that it is like a quadratic equation. It is in the form ax squared plus bx plus c is equal to 0. However, that equal will be changed to an inequality sign like less than, greater than, less than or equal, greater than or equal, or not equal sign. In our given example, x squared minus 3x minus 4 is greater than 0. It is considered a quadratic inequality because the expression on the left side contains a polynomial whose highest degree is 2. And it contains an inequality sign which is greater than. On our second example, m squared minus 5m plus 6 is less than 0. It is also considered as a quadratic inequality just like our example in example 1. However, in x squared plus 8x plus 12 is equal to 0, it is not considered a quadratic inequality. Thus, it is considered a quadratic equation. And quadratic equation has an equal sign in between, not a less than, greater than, or less than or equal, greater than or equal, or not equal. For the nature of the solutions of the quadratic inequality, we have here R1 and R2. So let R1 and R2 be the roots of the quadratic expression on the left side of a quadratic inequality. R1 is the lower root while R2 is the upper root. So we have here the following conditions for the nature of the solutions of the quadratic inequalities. So let's say we have ax squared plus bx plus c is greater than 0. Then the solution set will be x such that x is less than R1. R1 is considered the lower root, or R sub 1 is considered as the lower root, the one lower between the two roots. Or x is greater than R2, given that R1 and R2 are not equal with each other. We also have ax squared plus bx plus c is greater than or equal to 0. So the solution set will be x such that x is less than or equal to r sub 1, or x is greater than or equal to r sub 2. The difference between the two solution sets is the presence of the equal sign on the second condition rather than the elimination of the equal sign on the first condition. On our third condition, ax squared plus bx plus c is less than 0, the solution set will be x such that r sub 1 is less than x less than r sub 2. The solution set are those numbers in between the two roots. For ax squared plus bx plus c is less than or equal to 0, x is such that the solution set is x such that r sub 1 is less than or equal to r sub. The solution set will be x such that r sub 1 is less than or equal to x less than or equal to r sub 2. Same difference as we saw on our first and second condition with regards to our third and fourth condition. The presence of equal sign makes it differ on the solution set of the third condition to the fourth condition. Now, let us now solve for quadratic inequalities. The following steps are suggested in solving quadratic inequalities. First, write the corresponding quadratic equation of the quadratic inequality. Number 2, factor the polynomial of the left side of the quadratic inequality. Number 3, determine the value of the variable in the equation. The value values will determine the meaningful numbers. Number 4, divide the number line into 3 regions. The fifth step is to construct a test point table and select a set of values from each of the 3 regions. Number 6, graph the solution of the inequality. 7, give the solution set of the inequality. And the last one is to check the answer. For checking, it is optional since we already construct a test point value that will determine if the points, if the numbers within that region are solution set or not of the quadratic inequality. So we have here example number 1. Find the values of x in the given quadratic inequality. X squared minus 7x plus 10 is greater than 0. So our first step is to write the corresponding quadratic equation of the quadratic inequality. So the greater than on the expression on the quadratic inequality x squared minus 7x plus 10 is greater than 0. The greater than there will be replaced by equal, so that we will be solving the value of x first to get the meaningful numbers. Step number 2, factor the polynomial on the left side of the quadratic inequality. So the left side of the quadratic inequality is a quadratic expression x squared minus 7x plus 10. So we're going to find the factors of x squared minus 7x plus 10. So we are going to find the factors of x squared and the factors of 10. So for the x squared, our factors is obviously x and x. Now, we will get the factors of 10, whose sum is 7. So there are only 2 pairs of factors in 10. We have 1 and 10 and 2 and 5. So if we add 1 and 10, the answer is 11, and when we add 2 and 5, the answer is 7. So we are looking for the factors of 10 that will make a sum of 7. So in this case, the factors that we need is 2 and 5. Remember that the sign of the third term is positive. So both 2 and 5 must have the same sign. We will follow the sign of the second term in the quadratic inequality, or the linear term, which is 7x, and the sign of 7x is negative. Therefore, we will both put 2 and 5 in a negative sign, so x minus 2 and x minus 5. Therefore, the factors of x squared minus 7x plus 10 is x minus 2 and x minus 5. Step 3. Determine the value of the variable in the equation. The value values will determine the meaningful numbers. So, after we factored out x squared minus 7x plus 10 into x minus 2 and x minus 5, so we will use the zero property, wherein AB is equal to 0. If AB is equal to 0, then A is equal to 0 or B is equal to 0. So since x minus 2 times x minus 5 is equal to 0, we can conclude that x minus 2 is equal to 0 or x minus 5 is equal to 0. By the addition property of equality, so we add, for the first factor, we add 2 to the both sides of the equation. And for the second factor, we add 5 to both sides of the equation. So we come up with the values x is equal to 2 or x is equal to 5. Therefore, the meaningful numbers that we're going to get for the division of the number line later to get the regions are 2 and 5. So 2 and 5 are considered as the meaningful numbers. Number 4, divide the number line into 3 regions. Remember, 3 regions is the maximum number of regions in the number line. As we divide it using the meaningful numbers, the minimum number is 2. Why 2? Because there are some quadratic expressions whose roots are 1 real equal. So when we talk about 1 real equal, so maybe it is a perfect square trinomial. So in that case, there's only two divisions, region 1 and region 2. However, in our given example, we have three regions. And the numbers that we're going to divide in the regions are 2 and 5. Since we got it from step 3, and we said that the meaningful numbers will be the one to be used in dividing the number line into three regions. So we separate the regions in our meaningful numbers. So we have 2 and 5. So we can now name the regions as region 1, region 2, and region 3. The region 1 are those numbers below 2. So from 1 down to negative infinity, this is considered region 1. For region 2, these are numbers in between 2 and 5. So region 2 consists of numbers between 2 and 5, therefore it is from 2.01 up to 4.999. And as long as it does not reach 5 or does not reach 2. For region 3, those are numbers above 5. So 5.01 up to positive infinity. So that we don't able to make it more difficult for us for substitution later, we will use integers as the test point values, which will be discussed on our next step. So step 5, construct a test point table and select a set of values from the three regions. So as what I've said a while ago, we divide the number line into three regions, region 1, region 2, and region 3. So we get the test point value or the test point value for those particular regions. So for region 1, those numbers belong 2. So we get 0, so that later on when we solve, it's not difficult for us to solve if the value of x is 0. For region 2, numbers in between 2 and 5, so we get 3. And for region 3, those numbers above 5, so we get 6. So it is easier for us to solve later to substitute values if the values are integers rather than parts of the whole real numbers like the decimals or fractions. But however, there are some cases that we need to use fractions, especially if the if the meaningful numbers are only one up higher or one value lower. So for example, 2 and 3, 3 and 4, 5 and 6. But in this case, we have 2 and 5. So we get in region 2, we get 3. So from 2.01 up to 4.99. So our integers that belongs to 2 and 5 are in between 2 and 5 are 3 and 4. So we get 3 as a test point value. So we will now substitute the test point values to the given quadratic inequality x squared minus 7x plus 10 is greater than 0. So first up, we have x is equal to 0. So for x is equal to 0, we substitute x squared minus 7x plus 10 greater than 0, the original inequality. We substitute x with 0. So we have 0 squared minus 7 times 0 plus 10 is greater than 0. 0 squared or 0 times 0 is 0, minus 7 times 0 is 0, plus 10 is greater than 0. So by MDAS, we follow addition or subtraction from left to right. We have 0 minus 0 plus 10 is greater than 0. So 0 minus 0 is 0 plus 10, we have 10 greater than 0. In our quadratic inequality, we arrived at an inequality 10 greater than 0. And this is true since all positive numbers must be greater than 0. Therefore, the inequality 10 greater than 0 is true. For x is equal to 3, so the region 2 already, we again write the quadratic inequality x squared minus 7x plus 10 greater than 0. So we have 3 squared minus 7 times 3 plus 10 is greater than 0. So we follow first the MDAS rule, PEMDAS rule rather. So we have to extract first the exponent, then followed by multiplication, and then the addition and subtraction. For exponent, we have 3 squared, which is equal to 9. Minus 7 times 3, it's 21, plus 10 is greater than 0. Then we follow the addition and subtraction rule. So 9 minus 21, it's negative 12, plus 10, it results to negative 2 greater than 0. And negative 2 is greater than 0, it's false, since we all know it is truth that all negative numbers must be less than 0. Therefore, negative 2 is greater than 0, it's considered false. Number 3, x squared minus 7x plus 10 is greater than 0. So we substitute again the value of x, which is 6. So 6 squared minus 7 times 6 plus 10 is greater than 0. 6 squared, it's 6 times 6, so we have 6 times 6 is 36, minus 7 times 6 is 42, plus 10 greater than 0. So 36 minus 42, it's negative 6 rather, plus 10, which is equal to 4. So 4 is greater than 0 as region 1. All positive numbers must be greater than 0. So 4 greater than 0 is considered as true. Now, we complete the test point table in what you saw in our first slide in step 5. Then we will get the solution will be those regions which is considered true in the quadratic inequality as we solved a while ago. So those results with true are considered the solution set of the quadratic inequality. So we have region 1, 10 is greater than 0, that is true. For region 2, that is negative 2 greater than 0, which is false. And region 3, 4 greater than 0, which is true. Step 6, we're going to graph the solution of the inequality. So take note that we're going to graph now the solution of the inequality for us to see the solution set later, so that we will not be experiencing difficulty in writing the solution set of the inequality. So we have an open circle in 2 and 5. Since 2 and 5 are not part of the solution set, since the inequality is only greater than, and not greater than or equal. So for 2 and 5, the meaningful numbers are not part of the solution set. So open circle for 2 and 5. Then we put a line on the part of region 1 and on the part of region 3, since those are part of the solution set. So from below 2 up to from below 2, so from 1.99 down to the negative infinity, as well as from positive 5.01 up to the positive infinity, those are considered as the solution set of the inequality. We have a reminder that in graphing the solution of the quadratic inequality, please remember, if the meaningful numbers are part of the solution, put a dark circle above them. If the meaningful numbers are not part of the solution, put an open circle above them. Step 7, give the solution set of the inequality. So we refer to the nature of the solutions of the quadratic inequalities a while ago, and we conclude that the solution set will be x such that x is less than 2 or x is greater than 5. And as what I've mentioned a while ago for step 8, which is checking of the solution, this can be optional since we already test point values in every region. So it's no use for us to solve whether to check the solutions because we already tested it a while ago. And that ends my video on quadratic inequalities, and I hope you've learned something today. And thank you for watching, and please subscribe to my channel. Thank you.